Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another Math 1207 session. Hope you guys have had a good week and you're all settled. Quick announcement, today is actually the last day, people still trickling in here, to change your schedule, just so you know. So if you need to switch classes or you find out that you've registered for the wrong class and you need to actually go into another class, today is going to be the last day you can actually do that without any sort of major penalty or repercussions. So just be aware of that. Hopefully you guys know that you should be here. You've spoken to your advisors. I asked you to make sure of that on the first day. So make sure that that has been done. That being said, let's actually just jump into today's lecture. Let me share the Zoom with you guys. And just to make things run more smoothly, I'm going to turn off my camera. And you guys are allowed to turn off your cameras as well. You don't have to have them on if you don't want to. Okay, so here is what we started last time. Actually, I like the black background. Actually, let me restart this thing. Okay, there we go. And just a reminder, I highly encourage participation. So, whenever I throw a question out to the class, don't be too shy. You can jump in, you can type something in the chat box, or you can jump in audibly if you would like. Yes, so let's actually get into it. Let's just a little bit smaller. Okay. So last time we started talking about integration, and that's what the first phase of our class is going to be on. We'll be spending a while on this. There'll be 8 lectures, maybe 8, 9 lectures, where we'll be spent on nothing but integration. And by that, I mean about techniques of integration, right? How do you go about computing a certain integral? What are the strategies out there? As you will find by going through this course, integration is actually not as straightforward as differentiation. And you're going to realize that there are many more nuances and it is actually significantly more challenging. That being said, for Calculus 2, you really should never be in the case where you're faced with an integral and you have just no idea how to proceed. Things are still going to be very manageable, and I'm going to give you guys strategies and methods that will help you figure things out. That being said, putting them all together is where it's going to get confusing. But after I teach you all the techniques, we're going to go through around 8 or 9 of them. I will go back and do a summary of all the integration techniques that we've done. And I'll also let you guys know when to choose which, how you'd actually use each technique, when you'd actually want to use each technique, etc. It all starts with the basic integration rules. So these are the guys that I expect you guys to know about. So these are some basic integration rules. That's basically what I refer to as a rule that will allow you to integrate a fundamental function. Like, here's how you integrate a constant. Here's how you integrate a polynomial. Here's how you integrate 1 over x. Here's how you integrate the function e to the x. Here's how you integrate the function sine of x, right? So there are some rules that tell you how to deal with specific functions. Here's how you find the antiderivative of these functions, right? So these are the basic rules. And yeah, you should have a bunch of them memorized. Otherwise, things are going to be quite difficult. Then we also mentioned that substitution was probably the last sophisticated technique you learned in Calculus 1. So towards the end of Calculus 1 at some point, either the last topic or the second to last topic that you would have learned is integration by substitution. Technically what this guy is the reverse of the chain rule, and it allows us to figure out what an integral is by replacing a certain expression with a single variable, and in doing so, it reduces that expression the original integrand to something where you can apply, hopefully, a basic rule. So that was substitution, and that's something I expect you guys to learn last semester. Then we went into the art of integration, right? So there is a strategy, there is a method to the madness, and I actually told you guys what the first 3 steps are, and these first 3 steps are always going to be the 3 steps that you go through first, right? So at the moment, you don't know that many integral techniques, so right now it's probably a non-issue, but eventually it will become an issue, knowing how to approach a particular integral. So there is a strategy I want you to have in mind. Step 1 is to try to apply a basic rule, which means you are going to see, do one of these formulas that I have memorized apply directly to the thing that I'm looking at? Yes, if there's a constant multiplier, I can always factor it out, but is there anything that looks exactly like one of these rules? So that would be step 1. Step 2 is to try to simplify so that you can apply a basic rule. So every now and then you'll get an integral that it doesn't look like a basic rule. However, algebraically you can simplify it, maybe through division or some other process, so that each individual term now will follow a basic rule. And then you can apply the basic rule. So in this case, the derivative of the integral of the constant helps you deal with that. The integral of 1 over x helps you deal with that. The integral of x to the n rule helps you deal with that. So that is always the second thing that you want to try. The third thing that you're always going to want to try is substitution, right? Substitution is the most basic integration technique of all the sophisticated integration techniques, which means whenever this guy works, chances are it's going to be the easiest technique to pull off. And as such, it's probably going to want to be, you'd want it to be one of the first things you think about, among the first things you think about, because if it can work, it'll be naturally easier to work than anything else. So you're going to want to try that third. And the first—
Can I interject a question?
Yes, sure.
All right. I was just wondering, for the integral of 1 over x, and that's x to the -1.
Yes.
Why wouldn't it be, like, wouldn't it technically be x? Oh, it would be x over 0. That doesn't make sense, right?
Exactly. You can't divide by 0. Yeah.
Okay.
So when the x has the power -1, that is the only case that this formula cannot handle. So formula 2 for the integral of x to the n, it works in every scenario except that one, except where n is -1. Because when n is -1, the denominator would be 0. So yeah. So the 1 over x scenario is dealt with by rule 3. So the basic rule 3 is what you'd use in that scenario.
Thank you.
Right. Now, that being said, these 3 things, if you're faced with a random integral, these are the 3 things that should go through your mind first and in that order. Does a basic rule apply? Can I simplify it so that a basic rule can apply? And 3, could a substitution work? And it's not always super obvious that a substitution is going to work. I know what you've probably been told in Calculus 1 is that, oh, just make sure that whatever you substitute, you can see its derivative elsewhere in the function. So if I have an x squared, if I differentiate that, I get 2x. And if I ignore the constant factor, I see x dx. And here's an x dx over here. So as long as you can see the derivative, you know the substitution is going to work. That is not true in general. So it's a little bit trickier in general to know if a substitution is going to work. But by doing a lot of substitution, you'll build up a certain intuition. You'll kind of know, okay, if I replace this, I can actually finagle things a little bit to get it to work out. We'll do some examples of that for sure. Yes, now step 4, and I put 4 in quotations here because it's not literally always the 4th thing. These 3 things, these are always the first 3 things you do every single time. Every period, single period, time, period, right? Now, once you are beyond these 3 steps, like if none of these 3 steps work, then all the other techniques I'm going to tell you about, they would come in no particular order. I'm calling integration by parts step 4, literally because it is the 4th technique that I'm teaching you, but not because it's always the 4th thing you will think about. As I mentioned, when I cover all the techniques that I'm going to cover with you, I will go back and summarize when you would apply which technique and in which order. But integration by parts was something that we introduced last time. So this is another integration technique. It is actually the reverse of the product rule. So if you look in what's in green in this line, that is actually the product rule. if I integrate both sides of the product rule and rearrange terms, eventually I could get to something that looks like this. This is called the integration by parts formula. Okay, now why is it called integration by parts? It's because the pieces in them, the U and the dV, they're referred to as parts. So the U and the dV are referred to as parts. And that's why it's called integration by parts. Right? Find the two parts, find the U part and find the dV part. Okay, so it's called integration by parts. This allows you to do an integral where you have one function or one part times another function or another part. And then the idea is I can do this integral on the left by computing this expression on the right. You will also notice that this expression on the right has its own integral involved. The idea is, of course, being, hopefully, the integral on the right side of this equation is going to be easier to compute than the integral on the left side of this equation. Now, okay, so that's the formula, and I'm going to show you how to use it. So in this first example, I'm going to go through this example. You guys are going to watch me. I'm going to explain very slowly what I'm doing. Hopefully you guys can catch on, and we're going to do a lot more examples together. But for this first example, I'm going to walk through it. Okay, so just to be clear, let's say I'm going to test on a quiz and I see this integral pop up, the integral of x times e to the x, right? Now, what is the boy to do? Okay, so first thing, here's what I'm going to think. One, can a basic rule work on this guy? And you're going to notice no. And two, the second thing I'm going to think, can I simplify to use a basic rule? And you would quickly come to the conclusion that no here. What am I going to do with the x times e to the x? How can I actually simplify that and write it another way? 3, substitution. Now, you might be a little bit out of practice for substitution from Calc 1. However, that should soon be rectified after you start going through some of the homework problems, etc. So I'm just going to assume that you would eventually realize that no, that's not going to work out here either. Because of course, what are you going to substitute? U equals x? Well, as far as substitutions go, that is literally always a bad substitution. Substituting u equals x never makes anything better. You literally just rewrite all the variables that were x's before as u's. Well, would u equals e to the x work? Well, that would mean that x is ln u, your du would be 1 over u dv. And what are you going to do with the x? You're going to transform this to something more complicated. So substitution is not going to work either, okay? So I see this random integral. These are the first 3 things that go through my head in this order, but I'm quickly knocking them off. And this is something that you'll get used to doing, and you'll be able to do this quicker and quicker the more you practice, okay? But this is what goes through my head first. And then that's when I start thinking, oh, let's try by parts.
Professor?
Yes.
So
Yes.
x and e to the x could be considered to be separate functions. Is that the telltale for when to use integration by parts?
Yes. You're going to have to look at the integral in parts, in 2 parts, right? Yes. I wouldn't say that's the telltale sign, because there are times when that's not the case. So for example, if I ask you to integrate x times the sine of x squared, then yeah, technically you can think of this as 2 separate functions, which is 2 parts. However, integration by parts would not be how you do this integral, right? You would actually use a substitution here, right? So it's a little bit more nuanced than that, right? So it's not just because I see 2 random functions. That's not how I would choose. However, I'm in a situation where, and again, later on, I'm going to explain what you would look for, but I really want you to know all the techniques involved before I go through that explanation. But let's say here, I'm trying integration by parts because so far, none of the other things I know about will work. So for some reason, I get to the conclusion that I'm going to attack this using integration by parts. Okay, now that we know by parts, here is what we would do. Step one, the first thing you want to do is choose the parts. So in my integration by parts formula, there is a U part and there is a dV part. So there are two parts that I'm thinking to the integral. So once I have, I said to myself, okay, I'm going to do integration by parts on this integral. The first thing I need to do is choose the parts. So that's what I'm going to do. I'm going to choose the parts. So here what I'm going to do is I'm going to say, you know what? Let the U be X and let the dV be e to the x dx. So here I've chosen the parts, right? So the U part in my head is going to be X. The dV part is the e to the x, okay? So that's the first thing. I'm going to choose the parts, okay? So now what I'm going to do is, of course, find the other parts, because eventually I'm going to need to plug it into this formula. So I'm going to find the dV, the du, which is just me differentiating the x. And I'm going to integrate to find the v, which is just e to the x. So in this part right here, I differentiate. And in this part right here, I integrate. Now, why do I do that? Well, I know u and I know dv. However, in the integration by parts formula, I also need to know what I also need to know what v is, because that's right here. I also need to know what du is, because that's right here. So once I've chosen the u and the dv, I do have to compute what the du and the v are. So the first thing is I'm going to choose my parts, and therefore I would be able to figure out the other parts on the right side of the formula. Once I do that, I'm going to plug into the formula. Okay, so now I'm going to go down and I'm going to plug into the integration by parts formula. So my original integral, let's call it I, is x e to the x dx. This is going to be equal to u times v minus the integral of v times du. Right, so these are the parts from earlier. So here, this is my u, this is my v, this is my v, this is my du. Right, here is my u, and here's my dv. So the formula says the integral of u dv is equal to u times v minus the integral of v du. So once I've chosen my parts, I compute the du and the v. I now just go and plug into the formula. So let me actually rewrite this here, just clean this up a little bit. So basically what I get is x e to the x minus the integral of e to the x dx. And so my original integral, I can compute this integral by computing this expression. Now notice that that expression has another integral. Once I see a new integral, I start the process over. Like I said, every time you see an integral, you go through this process in your head. You are going to start the process over, okay? So when you see this, start the process again. Every time you see an integral, you go through this process. So one, is there a basic rule? Is this a basic rule? And hey, yes, it is. So it turns out that the integral on the right side is now actually a lot easier than the integral on the left side. And once I notice that, well, now I just compute the integral. So it's x e to the x minus the integral of e to the x is e to the x plus c. And so I've computed that the integral of x e to the x dx is that integral. Okay. So I suppose I could make this into 3 steps here. So the third thing, after you plug into the formula, compute the integral on the right using this is not like an official term, art of integration form, a strategy.
Professor,
Yes.
when you're differentiating u into du, how come, like for this question, for example, it's 1 dx.
Yes.
So you put the dx in when you're plugging into the formula, but how come when you're finding the integral of dv to v, you don't put the dx in anymore?
Because d is already, d represents a derivative has been taken. When I'm going to v, it means I'm doing the integral, so I'm getting rid of all derivatives, right? So this comes from the fact when I had u equals x, what I did was I took the derivative with respect to x of both sides, and then I multiplied across by dx.
Right.
Now, when you're integrating, it's like you're going from this process to backwards. And so you're going to end up in a point where there are no d's left over because you're doing the integration.
Okay, so that's why you take out the dx.
Yeah, so here the dx gets removed because I actually did integration here.
That makes sense. Thank you.
So to go from dv to v, I do integration. So all the d's disappear. To go from u to du, I actually had to do derivatives. So you get a d appearing from the Leibniz notation.
Thank you.
Any other questions on this? Okay, so here's a question for you guys. How do we choose the parts? Because here's what I want you to notice. Okay, so I did this and it seems like most of you understood what happened, but here's what I want you to notice. Here's something worthy of note. Notice if I had made the choice suppose I started this out going u equals e to the x and my dv equals x dx, right? So I chose the parts differently, right? I see x e to the x, and instead of choosing the x as the u, what if I chose the e to the x as the u, right? What if I made that choice? Would I still get to the answer? So if I take du, that would be e to the x dx. If I integrate this to find v, that's going to be x squared over 2. And if I plug this in, this would mean that my integral x e to the x dx would become u times v minus the integral of v times du. And what you're going to notice about this new integral, it's more complicated than the original. Okay, so when it comes to integration by parts, there is such a thing as a bad choice, an incorrect choosing of the parts. So any idea of how you would choose the parts?
I would assume that u should be maybe like a simple, like it should be like x or like 3x, and then dv should be like something more complicated, so like sine x or x squared, or I don't know. That was just a guess.
Okay, but
Isn't u one that can differentiate down to 0, like if you keep going, like a polynomial?
those are all great, but here, what would you do with this example? That's something we would do in integration by parts. Who's easier here? Who would go to 0 when you repeatedly differentiate? Nobody. So no, so those don't work. Those are good guesses though, but it turns out if you've done enough problems, you'll realize that you'll end up in situations that those strategies do not work. And I do see someone mentioning in the comments, in the chat box, there's a mnemonic that you can use. It's called liate, right? Liate, it's a very weird word, but let's actually talk about what is liate, right? Well, the L in liate stands for logarithms. The I in liate stands for inverse trig functions, or let's just say inverse functions in general. Could also be like something like an inverse hyperbolic function or something like that. A, now this is the weird one. It stands for algebraic, which is a misnomer. Algebraic isn't the right word, but what they mean by this is polynomials. T stands for trig functions. And E stands for exponential functions. And how does this actually help us choose the parts? Well, here's how it's chosen. It's on like a spectrum where L is kind of towards the left and E is kind of towards the right. And along the spectrum is on the left side, the guys towards the left gets to be U first. Whereas the guys towards the right gets to be U last. What do I mean by gets to be U first versus last? I mean in terms of priority. When you have two different classes of functions, right? If you have two different, here's another example we're gonna do, but I'll do it a little later. Let me push it down. When you have two different classes of functions, how do you actually make the choice? So in the example, so the earlier example, I had the integral of x e to the x dx. What you would notice from that is that my x would fall in the A category. My e to the x would fall in the E category. According to liate, this guy gets to be U. And so obviously you would set U equals X and the other guy gets to be dV. Okay, so this is how, I wrote that word because I was avoiding the chat box here. So let me, actually, that's kind of scrunched up. Let me get rid of that. So the dV gets to be the e to the x dx, right? So you actually make the choice based on the category of function that you're looking on. Okay, now, why is this the best method? There really isn't, I mean, yes, you can go through and you can kind of reason through the strategy here, but essentially this was just a mnemonic that someone came up with on a statistical basis. We just do a lot of problems and we just realized through trial and error, you know what? This order seems to be the best order. When we choose in this order, we normally get the problem correct. When we choose in another order, we normally get into a worse situation. So it's not always something that you would be able to eyeball the function and be like, oh, this guy's gonna be easier to deal with than that guy, and so let's do this guy. Okay, but liate is a nice mnemonic that actually tells you how to make the choices in integration by parts. So you see a random integral, of course, the first thing you're gonna think, can I apply a basic rule here? Can I simplify it to apply a basic rule? Would a substitution work? No, then I have to try something else. One potential thing you can try is integration by parts. Once you know you're choosing integration by parts, you now have to choose the parts. You have to pick someone to be the u, you have to pick someone to be the dv. How do you make that choice? Liate. Liate
I
is
have
how
a
you make the choice.
question.
Yes.
I learned it LIPET. So if you have a problem with trig and exponential functions, how would you
Well,
decide?
that's because that's here. Your P would just be here, right?
Oh, right. Sorry.
Right. So but some people don't like the sounding of lipte. Lipte, like it sounds very weird, right? So some people put an A in place of the P. Right. So algebraic means polynomials. So P in that sense is the same. Another way people memorize this is by the word lipet, Lipet, and that's okay as well, because it turns out that the T and the E can actually have the same priority. You can choose either one of these to be first or second. However, in my experience, liate is actually the most common one, but lipte or lipit are also used, and you would actually get the same answer using those guys.
Professor? Oh, sorry.
Yes.
You go.
Sorry. What happens if you have a function that has both trig functions and exponential functions, and you have to make one the v or the u and one the dv? Because if they're about the same priority, what do you do then?
Oh, you mean if you have a T and an E?
Yeah.
Then it's up to you, really. Either way is going to work out.
Yeah, that built off my question.
And let me put it in this way. If integration by parts would work out on that problem, then either way would work out. So the T and the E are actually the same priority. You can do either one first or second. You'll still end up with the right answer either way. But if you have like an A and an L or an A and something else, then the order actually really matters. Another concern would be the following. Here's something else that you might be wondering. What if I have two of the same kind of function, right? Like what if I have two different trig functions, right? How do I deal with that scenario? It turns out that that's a little bit more nuanced, and I would rather do that after I teach you a few more techniques also. So there's the canonical example for something like that is to find the integral of secant cubed. It turns out if you wanted to integrate the function secant cubed, the most common strategy used is to rewrite it as secant times secant squared. So you write it in two parts and you use integration by parts. However, secant and secant squared are both in the T category. How do you make the choice when both functions are in one category? That's another concern you might have. And we will deal with that later. However, if you have two different categories of functions being multiplied together, and you have determined that integration by parts is the viable option, then this is how you would choose. Other scenarios not covered by liate, these guys are a little bit more nuanced, and really I should teach you a few more techniques before we actually deal with those nuances. Okay, that being said, let's actually jump into another example. And since I very slowly went through this example, we're gonna go a little bit more quickly through this one. And I'm actually gonna want your input on this one. So here's an integral. So you see this integral. This shows up on the quiz on Friday. What do you do? Integral of x squared times ln x. What do you think?
We have a quiz tomorrow?
You have a quiz every week.
Oh.
Yeah, that's in the syllabus. Recitations are for quizzes. That's how we're running it. So you see this guy on a quiz tomorrow. What do you do? Panic. No, that's not what you do. What do you do? What do you think?
You go through the steps and see if you can use a basic rule, simplify.
Exactly. Yeah, so does a basic rule work here? No. X squared times ln x, of course, that's not a basic rule. Can I simplify this? Not really, right? X squared times a log. Nothing really to do. I can't cancel anything, can't factor anything out and maneuver anything. Would a substitution work? I mean, what would your substitution be? Yeah, so those three steps don't work. So, okay, integration by parts is what you would choose here, especially since at this point you don't really know any other technique. So yeah, so let's say we've settled on integration by parts. Now what? What do I do?
So according to liate, ln of x would be u, and x squared would be dv.
Correct. So once I've settled on integration by parts as the strategy I'm using, I'm going to have to choose my parts. According to Liate, u would be the ln, and my dv would be the x squared. This means that my du is what? Hello? Du?
1 over x dx.
Mm-hmm. And my v?
X cubed over 3.
X cubed over 3. That looks more complicated. Is it? Let's see. So our integral would look like what by applying the integration by parts formula?
It'd be ln x times x cubed over 3.
Yeah, maybe tell me the formula. What is the right side?
Oh, the right side is uv minus the integral of v du.
Right. So especially if you just learn a formula, you do want to actually use that formula every time. So you keep repeating the formula until you memorize it. Okay, so you want u times v. In this case, I'm going to actually write the x cubed first because it's going to look awkward otherwise. So my v I write over here and my u I write over here. Minus the integral of v times du. Now what I can do, I can clean up a bit, simplify this a little bit. I can factor out a 1/3, and then I have x cubed over x. That leaves me with x squared. So now I have another integral comes into play. Now what do I do?
Basic rule.
Basic rule. It's actually a basic rule. It looks like the integral of x to the n. So I'm just going to apply that basic rule. That gives me x cubed over 3 plus c. And so my integral is actually x cubed over 3. That cube is written a little big. X cubed over 3 ln x minus x cubed over 9 plus c. And that would be the answer. That's our integral. Questions on that? Okay, let's do another example. So you can take like a screenshot of that if you want, but we're gonna keep going. Another example, lots of examples. Okay, e to the x sine x. So again, yeah, we're gonna go through the process in our head. Is this a basic rule? No. Can I simplify it to look like a basic rule? No. Can a substitution work? No. Okay, so we've settled on integration by parts. How do we do it?
This is an T and an E, so does it not matter which one is U and which one is dV?
Yeah. So let's say we're following Liate for arbitrary reasons. So our U would be who if I'm following Liate? This is actually written backwards. This is an E and this is a T. So according to Liate, who would I choose for U?
Sine x.
And your dv is going to be e to the x dx. So my du, derivative of sine x?
Cosine.
Negative cosine.
Positive cosine x. Integral of e to the x is just e to the x. So my original integral, let's call this I, is going to be u times v minus the integral of v du. So here we have a new integral to worry about. All right, how do I do that integral?
Do you do another integration by parts?
Yeah, it's actually very similar to the original, right? So, all right, let's try to break this guy down. Okay, so u in this case, I choose to be cosine. My dv is the e to the x dx. Therefore, my du is going to be minus sine x dx, and my v is going to be e to the x. And then I'm going to actually plug that in. So then I'm going to open parentheses, very important, and put u times v minus the integral. Well, now it's going to become plus of v times du. And that brings me here, that brings me here. So now we have another integral. So we have another integral that we have to worry about now. What do we do?
Isn't it just going to be the same because that's the integral we started with?
Oh, wow, that is the integral we started with. So what does this mean? And we just keep doing this forever?
We're gonna just keep like going, getting.
We're just gonna keep going forever?
No, please no.
No, right? Please no, exactly. Yeah, so what do we do now? Does this just mean integration by parts doesn't work here? Because it puts us in an infinite loop?
Choose other parts.
Oh, you
Can we
think
bring
choosing
it?
the parts in the other direction would work?
Can we bring it to the other side?
You can bring it to the other side. It turns out that this now becomes, you'd realize, hey, this is actually the original. So notice what we have here. It's now just an equation. Essentially what I have is my integral is equal to e to the x sine x minus parentheses e to the x cosine x plus the original integral. So now it turns out I can exit this infinite loop by just plugging in my original integral and now solving it like an algebra equation, right? So what would that mean? Well, I would bring, this would be minus I on this side. I would add it to that side. So I would get 2I. And then I would just divide everyone by 2. And of course, we know there should be a plus c here, even though I'm being a little bit sloppy and leaving it off. And that's the integral. So yeah, this is a situation. This is a situation that's actually relatively common with integration by parts. Every now and then you choose to do an integration by parts, and what ends up happening is you end up getting the original integral back. When that happens, don't keep going. All you need to do is stop right there and then take that integral and move it to the other side, right? Of course, after you distribute parentheses and make sure the coefficients are correct and all that good stuff, make sure to clean up your algebra a little bit, then move it to the other side. At that point, once you get the original integral, you stop and you treat it like an algebra problem where you're just solving to make a certain thing a subject of the formula. Okay.
Can you factor out the e to the x also?
You could,
Okay.
but that's an extra step where there isn't really any benefit. So
Okay.
yeah, you could do this, factor out a common e to the x. However, in general, factoring is only useful when you want to simplify, maybe if there was a denominator that you wanted to cancel something. So in general, I wouldn't require that you have to factor.
Okay.
Because here, there's nothing to do after I factor. You know, it's just like I'm taking extra time to write something out. But yeah. Okay, awesome. That was another example. Let's do another example. So you can take a snapshot of that if you're moving slowly. This one, x cubed e to the x. Ideas.
U should be x cubed and dx should be ex.
Right, this here is an A category. This here is an E category. This means that if I'm doing integration by parts, and remember, in my head, I would have gone through the 3 steps. Is it a basic rule? No. Can I simplify? No. Can a substitution work? No. But basically here, I would end up with U is equal to x cubed. My dv is equal to e to the x. My du would be 3x squared. My v would be e to the x. This means that my original integral, call it I, is going to be equal to u times v minus the integral of v du.
So isn't du 3x squared dx?
Yes. I'm just seeing who's paying attention. Okay, so now we have this line. How do we deal with this new integral right here?
Integration by parts again.
Integration by parts again. Okay, so, and of course here your u would be x squared. Your dv would again be e to the x. So your du would be 2x dx. Your v would be e to the x. And so now I'm actually going to plug those guys in. X cubed e to the x minus 3 times u times v minus the integral of v du. And we have another integral to deal with. How do we deal with that guy?
Integration by parts.
Integration by parts. Okay, so, all right, let's do this a third time. All right, okay, so u is equal to x. Your dv is equal to e to the x dx. And this is actually the first example that we did. So, I mean, you know, can go through this quickly. Okay, so, all right. Now we end up with x cubed e to the x minus 3, open parentheses, x squared e to the x minus 2, open parentheses, u times v minus the integral of v du. And at this point, we know what that integral is right away, right? So that's just actually e to the x. So what we would have here is x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x plus c. So that comes from me actually distributing the 3 here. 3 times this, 3 times this, 3 times that. And of course, there's the 2 multiplies out there as well. And so, yeah. So now I'm actually slowly introducing you to the various cases that you can end up in integration by parts. I would say there are 3 main classifications to an integration by parts problem. Some integration by parts problems, more straightforward. You hit it with integration by parts one time, you get an integral that's a basic rule, pretty easy peasy, you just have that. Okay. There's another scenario though, which was illustrated by this one. This I call a revolving integration by parts, not an official term. It's the kind of integration by parts where you do it, but eventually end up with the original integral popping up. It revolves on itself. The strategy for dealing with that is to stop once you see the original integral pop up and just move it to the other side using algebra. The calculus is done at that point. A third situation is something where you have to use integration by parts repeatedly, right? So these guys show up every now and then as well, where you hit it with integration by parts, you get another integral where you're gonna have to hit it with integration by parts again, you get another integral where you have to hit it with integration by parts again. Okay. So that's another scenario. but hopefully you're getting used to the integration by parts idea. Let's do more examples. So we really
Sir?
want to get, yes,
Can I ask a quick question about the last one?
sure.
I was just wondering how come in the first step that you took the 3 out before you did the rest of the integral? Yeah, like right there, yeah.
Yeah,
Mhm.
what about it?
So when you got du to be 3x squared dx, when you put it into the formula, why did you take out the 3 before doing the rest of the integral?
Just to make it easier on myself, I guess. I mean, if I left it inside, there would be no difference. I would have a 3 here and a 6 here.
Okay.
Yeah,
Okay.
that's just for aesthetic reasons. There's no reason that I just normally when you want to do an integral, factoring out a weird constant is just going to be a thing that you would tend to do. Knee-jerk reaction.
Thank you.
If you left the 3 in there, it wouldn't make a difference. You would just have this 3 already pre-distributed. Okay, let's look at the next example. X to the 5th e to the x. What do you guys think we're going to do here?
Can we just do the same thing as we did last time? Like just keep doing
Yeah, how many integration by parts do you think this is going to take?
5?
5. Looking forward to it?
No.
No, nah. Okay, nah. Right? Gotta be a better way. Okay, I hear you.
Is it because they're both exponents?
No, it's because
Or the polynomial? Never mind.
here we have the x to the 5th, which means that's going to be your u. You'll need 5 integration by parts. Notice what happened in our last example. We had an x cubed, and it required us doing integration by parts 3 times. One integration by parts brought us to where it's an x squared, another one brought us to where it's x, and then another one kills the polynomial altogether. Like I would have to use integration by parts 3 times to break down the x cubed to the point where the polynomial isn't there anymore, right? Because I'm differentiating and reducing the power by 1 each time. Now, if you look at x to the 5th e to the x, you'd realize that you'd need to do integration by parts 5 times to do this, because you do it once, you're going to get an x to the 4th. Do it another time, you get an x cubed. Do it another time, you get an x squared. Do it another time, you get an x. Then do it another time, the x is going to disappear. You would have to like all these nested parentheses. So here we have 2 nested parentheses. You're going to end up with like 4 nested parentheses. Lots of algebra, a lot of room for error, and it's just not going to be a fun time either. So there's got to be a better way, and there is. Introducing something that's called tabular integration. So this is a variation on integration by parts that I'm going to teach you guys. AKA, it's called the DI method of integration, where D stands for derivative, I stands for integral. Okay, so integration by parts, it's a versatile technique. You can end up in many different scenarios. And sometimes you'll end up in a scenario where doing the integration by parts, even though yes, you can do it with integration by parts, it's just really annoying to pull it off because it expands too much. There are going to be too many nested parentheses. You have to be expanding all these parentheses. It's going to be room for error, and it's going to be algebraically, it's not going to be really nice to actually do it. So there is a variation on the integration by parts method, and it's called tabular integration. So let me move to the next section because I made a separate thing for that. Tabular integration. Okay, so this is something that we are continuing now to. Okay, so tabular integration is a way to streamline integration by parts. So integration by parts, everything I told you is still true, it's still awesome, but there are times when you might want to do something slightly differently. So let's actually look at when such a time might be. Okay, so here's how it's going to work. So this, again, is a variation on integration by parts. It's a way you can streamline integration by parts. And it's particularly useful in scenarios where you'd have to repeatedly do integration by parts to the point where it's becoming really annoying, right? Like the x to the 5th e to the x, right? You don't want to have to go through integration by parts 5 times. So there's actually a nice way, okay? Now I'm going to explain this method to you. Now I did write down notes here, pretty much explaining everything that I'm going to be telling you right now. So you don't really have to write down these notes all together. So for now, just listen to what I'm saying and describing the method. And then once I publish the PDF of this, you guys will be able to read through the notes more slowly and more carefully. But if you watch what I'm doing here, you should catch on to it. We're going to do some examples. Okay, so here is how this method works. So let's say you have an integral, which here we're calling the integral of f of x times g of x dx. Okay, so I have an integral of big F of x times big G of x dx. And suppose I'm considering the f function to be the u and the g function to be the dv. Okay. How does the tabular method work? Well, as the name suggests, you actually use a table. So what you're going to do is below this, you're actually going to start drawing a table. Okay, so you're gonna start writing a table below the integral, okay? And here's what we're going to do. So we're going to repeatedly differentiate in the left column. The u is in the left column. Remember, when we have u, we differentiate it to get a du. And we're going to keep doing this repeatedly in the left column. So this is the d column, right? That's where the d in the di method comes from. So I'm going to differentiate f prime, f double prime, f triple prime, etc. Dot, dot, dot. Eventually, I'm going to differentiate n times f to the nth prime. In the right column, this is the dv column. This is the I column, the column that we're going to want to integrate. Now, I'm going to use the subscript notation to indicate integration. So this here, g sub 1, is the first antiderivative. G sub 2 is the second antiderivative. G sub 3 is the third antiderivative. Dot, dot, dot. Then I would, of course, end up with g sub n is the nth antiderivative. So you're going to construct a table here. No, you just need f prime. You don't need to write the dx. Okay, so I'm going to write down, I have a function, keep differentiating it. Then the other function, the dv part, keep integrating it. You're going to construct a table like this. Now here's the kicker. You are going to do a product of the functions along the diagonal. So you're going to take this times that, this times that, this times that, this times that, etc. You're going to have something here times that. And then finally, you're going to end with this times that to end, right? Now, what do you do with these products? Well, you're going to alternate signs. So the first product, you attach a plus sign factor to it. The second product, minus sign. Third product, plus sign. Second product, minus sign. And so on and so forth. Here, we don't know what it's going to be. It's going to be plus or minus. And then you're actually going to switch signs again. For this one, this is going to be plus or minus sign attached here. So what the sign is at the end, I don't know. It will depend on how long the table is. But I'm going to attach all these signs. And what I'm going to end up doing is I'm going to end up, let's do this down a little bit. So what I end up doing is the following. I'm going to end up with the integral of big F g dx, and that's going to be equal to, I'm going to go through and multiply all these products. So I'm going to have the f times the g1 minus f prime times g2 plus f double prime times g3 minus f triple prime times g4 plus dot, 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 etc. I'm going to end up with a sign, say minus plus time of f to the n minus first derivative times gn. And then I'm going to end up with the last term, which is going to be plus or minus the integral. On the last term, I'm going to throw that integral back in. And it turns out this actually models repeated integration by parts. Because you have these nested parentheses and there's a negative sign in your integration by parts formula, when that negative sign gets distributed through all the parentheses, it starts alternating all the signs back and forth. You'll end up with a cascade of functions looking like this, and you end finally with an integral on the last leg. Yeah, was there a question just now?
Yeah, I have a question.
Yeah.
So you do FG1, and then minus F prime G through or G2. So
Yes.
the minus that, so I was just confused, like on the table, the plus goes, so it's, the plus goes before.
Yeah, the plus attaches to this arrow. Like
okay,
I'm
so it
labeling
goes
each
before.
arrow.
Okay, got it.
Yeah. So it starts out with a plus F times G1 minus F prime times G2 plus F double prime times G3, etc.
Perfect, thank you.
Okay. Now, a question you might have is, how long should the table be? How long do I keep doing this? Do I do this forever? How do I know what n is? That is a reasonable question. And you stop the table when one of these three conditions are fulfilled. One, the first condition is if the derivative in the guy in the derivative column eventually hits 0, right? So if, for example, your f is a polynomial and you keep differentiating it, you will eventually hit 0. Once you do that, you would stop, right? Another situation you can find yourself in is if the product along a row is easy to integrate by deal with, I mean integration wise. Then you can stop the process there. A third situation is if the product along a row is a constant multiple of the original integrand. So that's the original guy you started with. If you see that guy showing up again, you can stop the process at that point. Now, once you stop the process and you apply this formula, which I know writing it out looks confusing, but if you can construct it from the table, it's a little bit easier. You will be able to do integration by parts. So that's the formula here. But memorizing that formula, I don't think is very efficient. Memorizing the method. So let me actually show you this with a few examples so you can see. We've
Sorry.
actually done, yeah.
Could you go back to the steps 1, 2, and 3 for when you stop, just so I could jot it?
Oh yeah, take a picture.
Can I jump in with a question?
Yes.
So when you're doing the table and then let's say you get to the end, let's say that the derivative is 0 or one of the other rules, the last step is to go back to the last one and make it an integration by parts?
It depends. Like what this integral would look like, once you get that guy, the last integral, you will deal with it like just any other integral. So you go through the strategy again, apply a basic rule. Do I need blah, blah, blah? But you shouldn't need another integration by parts. If you terminate at this point, it should not be the case that it requires another integration by parts, because that would mean you should have gone a row further.
Okay.
So the integral that ends here, you will need to do it by another method. But the idea is hopefully it's a lot easier.
Okay. So like that's kind of like a tell, like if it's an integration by parts that we could have kept going?
Yes.
Okay. Thank you.
Okay. So we've actually done these 3 examples before. So I'm actually going to redo them using the tabular method so that you can see how it would work. And then we're going to do this guy, go back to the x to the 5th e to the x. And you're going to realize that it's actually not as bad as you may think initially. So let me move these guys out the way.
Can I ask one more question?
Yes.
In the third option for when the table ends, what do you mean by a multiple of the original integrand?
I mean literally that. If you see the same functions appearing, but some constant times those functions appearing, that's what I mean. A constant
okay.
multiple.
Thank you.
Yeah, it's a constant multiple. All right, so let me do an example so you guys can see this method in action, because just me describing it in words might actually be a little bit confusing. So I'm going to compute this with the tabular method. So how would that actually look? Okay, so we've done this already, so I'm not gonna spend a long time on it, but here's how it would look with the tabular method. X cubed e to the x dx. Again, I would have concluded that I want to use integration by parts on this, and I would just, if I want to use the tabular method, I would just draw a table. The x cubed would be the u. I would keep differentiating it. 3x squared, 6x, 6, 0. See that the u eventually hits 0? That means you stop. This means you're in case 1. Yeah, this is just for poetic effect. I do mean stop, just in case. Professor, what do you mean by the abbreviation STAAP? I'm just being theatrical. Okay, so I hit 0, so I'm going to stop the process. Now what I'm going to do is I'm going to go through the other column and I'm going to repeatedly integrate. Integral of e to the x is e to the x, integral of e to the x is e to the x, integral of e to the x is e to the x, integral of e to the x is e to the x. Now what I'm going to do is I'm going to do that products. This times this with a plus sign. This times this with a minus sign. This times this with a plus sign. This times this with a minus sign. Then that times that with a plus sign. So what would that actually look like here? So what that would end up looking like is the following. I would end up with I equals x cubed times e to the x times a plus sign. Then minus 3x squared e to the x. Then plus 6x e to the x. Then minus 6e to the x. Then plus the integral of 0 dx. Well, that's just a constant, isn't it? And so I would end up with the integral being x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6e to the x plus c. And you will notice that if you look back in your notes, that's the same answer we got last time. Right? So this is the tabular method. Notice that I do integration by parts repeatedly. This is equivalent to me doing integration by parts 3 times and multiplying out the parentheses. Okay, let's do this again. Okay, someone tell me how to do tabular method.
You would assign a u to ln x because it's a log, and then dv to x squared. So you kind of like switch around the table from last.
You'd have to actually switch the table, right? So you'd first write it in this order so that the table would work out. Then you are going to start drawing your table. Now what you'll notice is this is ln, which means when you differentiate it, you're never actually going to hit 0. You differentiate it once, you're going to get x to the minus 1. Differentiate it twice, you're going to get negative x to the minus 2. Differentiate it 3 times, you're going to get positive 2x to the minus 3. It'll never actually hit 0. So it means you're not in case 1. However, if I do the integration on this step, x cubed over 3, this is enough for me to stop. Stop.
Is it x
You're in
cubed
case
over
2
3
here.
or over 2?
This should be over 3. It's case 2, right? What is case 2? Notice that if I multiplied along this row, the product is equal to 1 over x times x cubed over 3, which is x squared over 3, which is easy to integrate. And that's how I know to stop. This means you're in case 2, which I mentioned up here. The product along a row is easy to integrate. So here, I know I'll never hit 0, and I'll actually never get a repetition, because once I lose the ln, it's never going to pop back up. So I'll never get back the original integral here. So instead, I'm looking for a row. The moment I see a row that, hey, I know I can integrate that easily, I would stop. So this process actually just goes one step down. So it's this times this with a plus sign, and then that times that integrating with a minus sign. And so this ends up being x cubed over 3 ln x minus the integral of x squared over 2 dx. You would actually now be able to integrate that easily. So this is over 3. I did it again. So this is now x cubed over 9 plus c. And again, you'll recognize that as the answer we got last time. So tabular integration can work in that scenario as well. Now we're almost out of time. Let me do it with the third scenario. And then what I would like you to do is to do tabular integration on the other scenario, the example that caused us to run into this. So here's another example. You might recall that this was the example that caused a repeated integration by parts, a revolving integration by parts. We can still make it work here. So what I can do here is, if I want to follow Liate, write this as sine x times e to the x. I would draw the table below it. Differentiate sine of x, I get cosine of x. Differentiate cosine of x, I get minus sine of x. Integrate e to the x, I get e to the x. Integrate e to the x, I get e to the x. Notice in this row here, this is actually -1 times the original integrand. This is what I mean by it's a constant times the original, right? If I multiply across, I get e to the x sine x, which is just, it's actually just the negative of the original. So that tells me I could stop the process here and just run through that algorithm. So this times this with a plus sign, this times this with a minus sign, this times this with a plus sign. And so what I end up with is I would be equal to e to the x sine x minus e to the x cosine x minus, and remember on the last, the one where you go across horizontally, you put an integral on that one. But this is the original, so you just move to the other side. And you actually end up with the answer that we got last time by dividing both sides by 2. So the tabular method can work in every single integration by parts method. In every scenario where integration by parts will work, the tabular method would also work. So in fact, what I want you guys to do is to actually do this example. And for next time, what I'd also like you to try, there's nothing else for me to teach you with integration by parts at this point. Also try, I'm going to put more examples for you guys to try. I had some more over here. Because watching me do problems is can be very different from doing your own problems. So I do want you to try these examples as well. It turns out that these guys are guys that we can do with integration by parts. Maybe. So lots of examples. So I really want to hammer integration by parts home. So I would, I'm going to leave these guys in the PDFs. We will start the next class by going through these examples. So yeah, do the x to the 5th e to the x with the tabular method. And if you want, you can do it with the regular method as well. So you can make a comparison for which one you would like more. In general, the tabular method will work in every instance that integration by parts will work. Although for some situations you might not want to use it, but there are some situations that lend themselves very nicely to the tabular method, such as x to the 5th e to the x.
So will the examples that you want us to do, are those the same as our homework, or are those in addition to the homework? Or...
No, these are different. These are in addition to the homework. I'm actually going to do these in class next time, but I actually want you guys to try them before next class.
So how do we find these then?
They'll be in the PDF when I post the video. If you want, you can take a picture of them right now.
Okay.
But when I post the video recording later, I will post a PDF of the notes in the video description.
So what can we expect on the quiz tomorrow?
Integration by parts. It's the only thing we've done since the last quiz.
So there won't be any hyperbolic trig?
When did we do? We did hyperbolics on Monday. So no, so it'll do both. Everything we, in general, quizzes cover everything I did since the last quiz. So whatever I covered on Monday and whatever I covered today. So you should know about hyperbolic trig functions. You should know about integration by parts. And of course, I might throw in some integrals with substitution just to make sure that you remember that. So integrals up to integration by parts will be on the quiz tomorrow. And yeah, I see the message in the chat. So if you want to have office hours after, I'll send you the link, okay? But yeah, that's it for today. So let me also mention here, quiz tomorrow. Hyperbolic trig functions. Of course, so know how to differentiate them, integrate them, all the formulas that I mentioned, and integration by integrals up to int by parts. Right. I already want you to start noticing where integration by parts would be useful. So I might throw an integral on the quiz that doesn't require integration by parts, just to see who would actually try integration by parts when they shouldn't. So that's actually going to be important for you to start distinguishing between when a method would be useful or not. In the meantime, I'll pause right here for 5 seconds so you can take a picture. 5, 4, 3, 2, 1, and then pause right here so you can take a picture. 5, 4, 3, 2, 1. But I'll post a PDF of these notes once I post the lecture video, and you guys know where to find that, and you can get it there. So it'll be good practice for tomorrow as well.
So, sorry, so is it required or recommended that we do those extra practice things?
It depends. How comfortable are you with integration by parts?
Okay, thank you.
Yeah, so I mean, if you're like, oh yeah, I got integration by parts down, then hey, practice less is your prerogative. I would attempt them though. And you can of course check your answer through Wolfram Alpha or something else. So you can know that if you're doing them right. I would say it's better than not to practice them. Okay, that being said, guys, that's it. That's all I have for you today. I will send you, the person in the chat who asked to meet me after, I will send you a link to a Zoom room for office hours. The rest of you, have a good night. Hopefully you had a good week. And I will, I guess, see you guys in the next one. If you have any other questions, if you go over this lecture and you have any other questions, any other issues, concerns, you can, of course, email me and let me know. That being said, good night, everybody. Thanks for showing up. Thanks for participating.
Thank you.
Thank you.
You're welcome. You're all
Thank you.
welcome. And I will see you guys in the next one. Ciao.